In this lecture, we will be discussing about design of beams on ETABS. So before this, you watch my lectures on design of beams for flexure, that is singly reinforced. Next, similarly, design of beams for flexure, that is doubly reinforced. Similarly, you watch design of beams for shear. First you watch these three lectures, then you move on to design of beams on ETABS. First you learn how to design a beam manually. Then you can easily move on to ETABS. First I will take you to ETABS. So go to File, Import ETABS.e2k file. So I have created a sample model for beam design. You just click on this beam design.e2k file, which will be sent to your Google Classroom. Open. So I will close this 3D view. See here, this is the model which I have sent to you as a .e2k file. I will be using this file for my beam design demonstration. So first and foremost thing is run your analysis. Only after analysis design will run. So first step is run your analysis. Only after analysis design will run. So I will remove these grid lines. So go to view, set grid system visibility. So grids will be turned off. Okay. You just run analysis. You save it by a file name beam design model. So before you run the analysis, you check it. In design, there will be a tab for live load reduction factor. Live load reduction factor. So in which you should select no live load reduction. You should select no live load reduction. So just I will unlock my model. So in case of design, here live load reduction factors. Yes, I have no live load reduction. You should select this option first. So click on OK, then run the analysis. So now tell me, what are the design parameters or design preferences will affect the beam design results? So design parameters or design preferences. So one is FCK. It will be your grade of concrete, and Fy. So it will be grade of steel, and BD, your size of beam. So B is your width of beam, and D will be depth of beam, and clear cover. It will also affect your beam design results. Next, reinforcement diameter. Reinforcement diameter. So these will parameters affect your design. So will affect your design. So reinforcement diameters, you please remember here, reinforcement diameters are not directly used in beams. So while defining cover to longitudinal rebar group centroid, where we have considered the diameter. So while defining the section cover to longitudinal rebar group centroid, there we have considered reinforcement diameter. I will show you. So while define section property frame section, I will take you to any one beam 300 by 800. Modify show property. Modify. See here. Cover to longitudinal rebar group centroid. So this 41 mm, it will be arrived based on clear cover, longitudinal bar diameter, and stirrup diameter. Okay. So next, till ETABS 16-17, you didn't have slab design options. So you are using, now you are using 22, ETABS 22. In this you have slab design option, concrete slab design option also. So till ETABS 16-17, you didn't have slab design options. So before that, it was available in SAFE but not in ETABS. Okay. So our next step will be concrete frame design preferences. concrete frame design preferences. So for which you need to check in design, concrete frame design, in which view bar revise preferences. So here you should first select IS code. So various codes are available. You are designing beam as per IS 456-2000. So in design code you should select IS 456-2000. Okay. So this is IS code. Next, multi-response case design. So this is not applicable. Next, number of interaction curves, number of interaction points, consider minimum eccentricity, consider additional moment, consider P delta done. So these options are related to your column design. Related to your column design. So next, gamma for steel it is 1.15, gamma for concrete it is 1.5. So these two are material safety factors. Material safety factors. Okay. So in concrete frame design preferences, the first and foremost thing is you should select IS 456-2000. Okay. Again, you should have this pattern live load factor as 1 and utilization factor limit. It should be 1. Okay. So next you click on OK. So next it will be design, concrete frame design. So view bar revise overrides. It is not highlighted because you have not selected any beam. So you select all the beams. So how to select all the beams? How to select all the beams which are in this view at once? So it is very simple. You go to select object type. Your object type should be beams. You go to select. You just close it. See, whatever the beams in this view, all the beams are selected. So you have 42 beams. See here, 42 frames selected. So once you select the beams, then this option will be highlighted. What option? Design, concrete frame design, view bar revise overrides. So next step will be concrete frame design overrides. Okay. Design, concrete frame design, view bar revise overrides. So current design section, it is size of the beam. Framing type, in this framing type you have three types: ductile, ordinary and non-sway. This is very important: ductile, ordinary, non-sway. So framing type, it will affect your beam design results. So in which you have three types. First one is ductile. What will happen if you select ductile? All beams are designed as per IS 13920. So all the beams are designed as per IS 13920. So it is only when if you applied earthquake loads, you should select this option. If you have applied earthquake loads, you should select your framing type as ductile, because all the beams are under this category are designed as per IS 13920. So next option, it will be ordinary. So in this option, design would be carried out as per IS 456-2000. So in this, all the beams are designed as per IS 456-2000. Okay. So I recommend this option, ordinary. So this is the ideal for beam design. While designing your beams, you should select ordinary. So in this, all the beams are designed as per IS 456. So next option, you have non-sway. So which is related to columns. This option, it is related to columns. So what will happen if you select a non-sway? So design would be as per IS 456-2000, and all your columns are treated as non-sway columns. So all columns are treated as non-sway columns. So here we are designing our structure only for gravity loads. So which are only for dead load and live load. The ideal framing type will be ordinary. So ideal framing type will be ordinary. So in framing type, I will select ordinary. Okay. You just click OK. So next step will be design combinations. Which means load combinations. So for which you go to design, concrete frame design, select design combinations. See, list of combinations. You have two combination. So you are designing your structure for gravity loads. You have two limit state. One is limit state of serviceability, another one is limit state of collapse. For limit state of serviceability, load combination will be dead load plus live load. For limit state of collapse, so it will be 1.5 dead load plus 1.5 live load. So design combination, you should select 1.5 times dead load, 1.5 times live load. It is very simple. It is already selected, so you just click on this 1.5 DL plus 1.5 LL. You just move to the left side. Now it is empty, so you just select this 1.5 DL plus 1.5 LL and you just click on this. Yes, your design combination will be 1.5 DL plus 1.5 LL. So you just click on OK. So once it is over, next you go to design, concrete frame design. You just click on start design bar check. Okay. So I will switch on the grids. So now I will choose this elevation 1 view. So go to elevation. So in elevation you select 1, apply, OK. See, this is the 2D frame. Okay. So next you go to design, concrete frame design, display design information. So in which you have various types of design output. One is longitudinal, total longitudinal reinforcing, total rebar percentage, shear reinforcing. Okay. So first I will select total longitudinal reinforcing. You just apply, OK. So just I will increase the text size, option, graphic preference. So instead of 8 I will go for 15, maximum graphic font size. Yes. So whenever I select longitudinal reinforcing option, so it will show the values of AST, area of steel, in mm square. Okay. So next I will select design, concrete frame design, display design information, in which next I will select total rebar percentage. You apply, OK. So now whenever you select rebar percentage, so it will give PT. Percentage of steel. Same AST, it will be converted to PT, percentage of steel. Okay. So I will check the next option. So next to design, concrete frame design, display design information. So next I will check shear reinforcing, apply, OK. So whenever I select shear reinforcing, so it will give ASV divided by SV values. ASV by SV values. So from IS 456, you know the formula. VUS equals 0.87 FY FY ASV D divided by SV. So it is in page number 73 of IS 456 2000. So it will give ASV by SV values. So these are nothing but ASV by SV values. So in one equation you have two unknowns. So here ASV is also unknown and SV is also unknown. So in one equation, two unknowns, it is not possible to solve. So ETABS, it will give directly ASV by SV values. So if we have ASV by SV as 332.53, then you can assume one. ASV or SV, and you can find one, and you can easily find one. Okay. So I'll show you the reinforcements, design, concrete frame design, display design information. I'll select total longitudinal reinforcing, apply, okay. See here, for beams, ETABS will give you results at 6 different locations. So this is top and this is bottom. At the top you have 3 results. So one is end 1, this will be mid, and end 2. Similarly, bottom you have 3 results. End 1, this is mid, bottom mid, and this will be end 2. Okay. For beams, ETABS will give you results at 6 different locations. If you take any beam, it will give results at 6 different locations. So next, you click on any one of the beam, you just click on this beam, you click mouse right button, see here, so here you have station location. So beam designed at a different location. So same single beam which is designed at a different location. So this is beam designed at different locations. So if you see this blue color, so maximum location of longitudinal steel is highlighted. So automatically ETABS will highlight maximum location of longitudinal steel. So this is maximum location of longitudinal steel is highlighted. So see here, it is by default 776. It will highlight to maximum longitudinal steel. If you just check any other beam, so it will automatically highlight the maximum longitudinal reinforcement. So I will check this beam. Sorry, I will check this one, which is the maximum 772. So I will select this beam, right click. So it will automatically highlight it to 772. If I select this beam, it should automatically highlight at 840. See here, you select this beam, right click mouse, so it will automatically select it to maximum value 840. Okay, you just click on. So this is the beam I was explaining. You select this beam, click mouse right button, you go to details. So this is very important. So in which you click flexural details. You click flexural details. So flexural details means for bending moment. For bending moment. See here. So beam is designed as per IS 456-2000. Here, first level, it is showing second. So which means second floor beam, and this is 300 by 800. So this is beam size. So combination ID, load combination. So this is governing load combination for design. So this is governing load combination for design. So this will be the overall length of beam. So this will be the total length of beam. So this one is live load reduction factor. So I have chosen no live load reduction factors. Next, my framing type ordinary. So because of which all the beams are designed according to IS 456-2000. If I was selected ductile here, in framing type, so here code will be IS 13920, because whenever you select a ductile frame, all the beams are designed as per IS 13920. 920. Okay. So here this will be the width of beam, and this will be depth of beam, okay. So I will remove this part. So I think I stopped here. Depth of beam. Next here, this BF. So this is width of flange. This is width of flange. Okay. So this will be applicable in case of T and L beams. So if you take T-shaped beam, so this is your width of flange, so BF, and this is your DS, depth of slab. So here DS is depth of slab. So this will be overall depth D and width of the beam B. So these two are useful in case of L beams and T beams. Okay. Next, so DCT and DCB. So effective cover to top and bottom. So these are effective cover to top and bottom. While defining section properties, we defined this value. While defining the section properties, we defined these effective cover to top and bottom. So next it will be material properties. So this is Young's modulus of concrete and grade of concrete M25 and Fy 500. Again for stirrups it is 500. So these are material safety factors. So for concrete it is 1.5, for steel it is 1.15. So this value it is for concrete and this is for steel. So next it is flexural reinforcement moment. So how you arrived this minimum rebar? So how you calculated 387? See here, for which if you refer IS 456 2000 clause 26.5.1.1 page number 47. So you have AST minimum. So it will be AS divided by BD equals 0.85 F5. So from which you can calculate the minimum rebar. So AST will be 0.85 multiplied by B into D divided by F5. So here 0.85 into B, width of the beam 300 multiplied by D. So depth of the beam, depth of the beam it is 800 minus effective cover 41, so 759. So it will be 759 divided by grade of steel 500. So you calculate this 0.85 multiplied by 300 multiplied by 759 divided by 500. So it will be 387. So this will be 387.09 mm square. So this is minimum AST. So next, you have this design moments. Design moment, it is minus 264.68 and factored it is minus 264.68. Okay, so here in design and factored moment, if you have negative sign, then it is hogging moment, hogging bending moment, or support moment. If you have positive values, then it will be sagging bending moment or span moment So here you have negative values. So for negative, the bending moment will be hogging. So for hogging bending moment, steel will be provided at the top. So you remember, for hogging bending moment, steel will be provided at the top. Steel will be provided at the top. See here. So because of this only, your steel will be written on top. So 776. How you got this 776? You just checked 387. This is minimum. How you got 776? So I will calculate that. So your design moment is 264. So you use this formula, AST equals 0.5 into FCK 25 divided by Fy 500 into 1 minus square root of again 1 minus 4.6 into your mu is 264.68 into 10 power 6. This is your mu design moment divided by 25 into 300 into your effective depth of the beam 759 square multiplied by 300 into 759. You calculate this, you will get the AST. So 0.5 into 25 divided by 500 into 1 minus square root of again 1 minus 4.6 into so 264.68 into 10 power 6 divided by 25 into 300 into 759 square. Multiplied by 300 multiplied by 759. So it is 868. So AST it is 868 mm square. So here it is 776 mm square. Why there is a difference? It is because of I am using pirated version of the software, not a licensed version. So because of which there will be some errors. Okay. So my manual calculation is 868 mm square, but in the ETABS I am getting 776. So nearly the difference is 100 mm square. Okay. So this is because I am using pirated version of the software. So here this factored mu3. So this is your ETABS analysis moment. This is your ETABS analysis moment. This is your mu. Okay, I will just show you. I will close this. So you remember the value. It is 264. You just cancel it. You go to display, force bar stress diagram, frame forces. You select M33 combination 1.5 DL plus 1.5 LL. You click on apply. Apply. Okay. See here. Here the value is 264 at this location. Yes, your bending moment value is minus 264. So this is ETABS analysis moment. So then go to design, concrete frame design, display design information, total longitudinal reinforcing, apply. Okay. Click on the beam, right click mouse. So go to details. So we are in flexural design. So we are into this. So 264. This is your ETABS analysis moment. So next TU. So this is your torsion moment. So this is your torsion moment. So here 0 indicates no torsion. 0 indicates no torsion. So next MT. How you calculate the MT? So MT equals TU. MT equals TU into 1 plus D by B divided by 1.7. So this is the formula to calculate MT, moment due to torsion. So this is MT is moment due to torsion. If your TU is 0, then automatically you will get MT as 0. Okay. The next, here you concentrate here, your design moment is, so here this value is mu3 plus mt. If you see here, your mu3 is 264.686, this value, plus mt is 0. So automatically your design moment will be 264.68 kilonewton meter. So nature it is hogging. So you know the formula, design moment equals analysis moment plus moment due to torsion. Moment due to torsion. Okay. So this is all about flexural design. Next we shall move on to shear design. Next we shall move on to shear design. So you just click here, shear details. Shear details. So shear details are for shear force. Shear details are for shear force. So in the beginning you have same details. So this already completed in flexure design. What is the section properties, material safety factors, material properties, same in flexural design. So next you need to concentrate here, it is design basis. So you first come here, design basis. So first VU. So this is VU is value from ETABS analysis. So shear force from ETABS analysis. So this is your tension reinforcement. You already know this in flexure design. You already know this value in flexure design. So this is grade of concrete. So this will be grade of concrete. Okay. So next Next thing will be so here you need to concentrate on this value AC concrete area, so which is B into D. So width of the beam 300 multiplied by effective depth of the beam 759. So you will get 227700 mm square. But here it is written in centimeter square. You divide this value by 100. You divide this value by 100. So which will be 227700 divided by 100. So it will be 2277. So this will be 2277 centimeter square. So this value. Next you have AG gross area. So which will be B multiplied by D. So B is 300 and overall depth of the beam it is 800. So 300 multiplied by 800. So it will be 240000. It will be in it will be in millimeter square. So initially it is in millimeter square. So divided by 100. So divided by 100. So it will be 2400. So it will be 2400 centimeter square. So it is this value 2400. Okay. Even though you have taken grade of steel as Fe500 for shear design it will take Fe415. So it is as per IS code. Okay. So we will move further. So next it will be this one, concrete capacity. So here first it is tau c. How you calculate tau c? So first you have AST. Your AST will be converted to PT, percentage of steel. So for which you observe table 19 of IS 456. So for M25 grade of concrete, you will record tau c value. You just revise the theory design of beams for shear. You will get to know the how tau c it is been calculated. So this is how tau c is calculated. Okay. Next. So here next is tau v. So next it is tau c. So tau C, how you arrived 0.42, which is equal to tau C multiplied by delta. So your tau C is 0.41, this value 0.41 multiplied by delta. So this value 1.032. So it will be 0.41 multiplied by 1.032. So it is 0.42. So it is 0.42. So this value 0.42. So next, how you got delta? So it is delta equals 1 plus 3 pu divided by AG FCK. Okay, so for which you refer clause 40.2.2 IS 456 2000 on page number 72. So let me open the code, page number 72. Yes, here you have the formula. Shear strength of members under axial compression. Delta equals 1 plus 3 pu divided by AG FCK, but not exceeding 1.5. So maximum value of delta is 1.5. So in the theory of design of beams for shear, we neglected this value. So it is very negligible. We neglected this value. We directly taken tau C value. Here ETABS will multiply, initially calculate tau C based on PT and FCK. It will multiply this tau C by delta. Then it will give you this tau C. It is 0.42. Okay. Next to tau V. This will be your tau V. So how you calculated this value? Tau V equals, you know the formula, VU divided by BD. So your VU is this value 187.509 into, it is in kilonewton, so 10 power 3 it will be converted to Newton, divided by width of the beam 300 and effective depth 759. So your tau V would be so it will be 187.509 into 10 power 3 divided by 300 into 759. So it will be 0.82. So it will be 0.82. So 0.82. Next it is this value tau C max. Here in IS 456 you refer table number 20. So tau C max value, it is 3.1 Newton per mm square for M25 grade of concrete. So let me check this. Yes, for M20 grade of concrete, tau C max it is 3.1. So I will remove this. Next, how you calculated this VC? So VC equals tau C BD. VC equals tau C BD. So tau C value is this value 0.42 multiplied by width of the beam 300 multiplied by 759. Okay, so let me calculate it. 0.42 multiplied by 300 multiplied by 759, so which is 95634. It is in Newton, so you divide it by 1000, so it will be in, now it will be in kilonewton, 95.63 kilonewton. So it is 95.63 kilonewton. Yes, this is completed. Next, how you calculated this Vs? So Vs equals, you know the formula, shear force Vu minus Vc, shear taken by concrete. So Vu is 187.509 minus 95.63. So it will be 187.509 minus 95.63. So it is 91.87. 91.87 kilonewton. So this is Vs, this is Vc, and this is Vu. So shear taken by steel, this is shear taken by concrete. For this, we need to design the shear reinforcement. For Vs, shear taken by steel, for this 91.86 kilonewton, for which you need to design the shear reinforcement. Okay, for which you have the formula, Vs equals 0.87 Fy ASVD divided by SV. Okay, so here Vs is 91.86 into 10 power 3, which is equal to 0.87. Fy is 415 into ASV into effective depth 759 divided by SV. So if you solve this equation, you will get ASV by SV as 335.4 mm square per meter. So this is your this answer, ASV by SV. So in this you can assume 1 and find 1. You can assume ASV as 2-legged 8 mm vertical stirrup. You can find SV, or you can assume spacing and you can calculate the ASV. So assume 1 and find 1. Okay, so this is how you can check your ETABS results for flexure and shear. See here, you have ASV divided by SV value as 335.4 mm square per meter. If I assume two-legged 8 dia stirrup, two-legged 8 dia stirrup. So ASV will be so 2 into 2 leg multiplied by pi into 8 square divided by 4. So it will be around 100 square. So your ASV will be 100 square. Okay. So 100 divided by SV equals 335.4. Okay. You calculate the spacing. You calculate the spacing. So here it is. Hundred divided by 335.4. So it is 0.298. 0.298. So this value is millimeter square per meter. So this will be in meter. You just multiply this value by 1000. So you multiply this value by 1000. So you will get 298, or almost it is. Almost your spacing is 300 mm. So you finalize to provide two-legged 8 dia vertical stirrups at 300 center to center. So this is your shear reinforcement. So now you need to check whether this will satisfy your minimum criteria and spacing requirements. So how to check the minimum shear reinforcement requirement? You have the formula ASV divided by BSV, which is equal to, sorry, I will just write it once again. So ASV divided by B into SV, which will be greater than or equal to 0.4 divided by 0.87 Fi. You first calculate the left hand side value. Next you calculate the right hand side value. Finally you should get left hand side should be greater than or equal to right hand side. Then only your shear reinforcement requirement will be satisfied. So this is for minimum shear reinforcement. So but what for spacing? You have three criteria. First is 0.75 times D. Next, second one will be 300 and third one will be calculated spacing. Again it will be 300 So you need to provide lesser among three values. So this is 300 and this will be 300 0.75 times your effective depth will be, I think, 759. So it will be 0.75 multiplied by 759. So it is 569. 569. So lesser among these three is, so your SV would be 300 mm. So you can provide this. You can provide this two-legged 8 mm dia vertical stirrups at 300 mm center to center spacing. So before going to this lecture, you watch design of beams for flexure and shear. Then only you will be able to understand these calculations. If you miss these two lectures, then it will be difficult to understand these calculations.